Harley Davidson Motor Company proudly presents this PhD service training program. This program is designed to help you provide better service to your customers while you increase your service proficiency, professionalism, and profitability.
You see, Art, when we build our motor-assisted bicycle,
Let's call it a motorcycle.
we're going to catch a lot of heat for changing the way Americans sound on two wheels.
Bill, you can't stop innovation. You've done the designs. I finished the patterns for the engine. My brother Walt's coming in from Kansas City, and my brother William's coming in to help us too. Once you finish figuring out the carburetor,
I'm done. This is it.
that's a tomato can.
A couple of holes, some tubing, it's a carburetor.
That's it. Well, that proves you're right, old buddy.
Well, a tomato can isn't quite enough for the V-twin of today. So as the years pass, development engineers continue to improve on the carburetor. In this program, we'll examine the theory behind the modern carb and how it contributes to engine power and performance. We're going to go over the basics of carburetor operation on the fixed jet carb, then focus in on the constant velocity, or CV carb. Since maintenance procedures are outlined in the current service literature, we'll stick to how the carburetor works. That's a complete subject all by itself. Before we get into the details of its operation, let's review the basic physical laws that make the carburetor work. These laws have been tested and proven, so don't worry if some seem a bit hard to grasp. Liquid takes the shape of its container. A contained liquid produces pressure in proportion to its depth. Liquid in two chambers that are connected will be at the same level in both chambers, unless there is a difference in air pressure on top of the liquid. Then the level will be higher in the low-pressure chamber. Air under high pressure moves toward air under low pressure if the two areas are connected by an enclosed passage. Air that travels through a constriction increases in speed and decreases in pressure at the point of constriction. This is the Venturi principle. A liquid can be atomized or broken down into smaller parts. We'll explain how these laws pertain to the carburetor throughout the program. Keep in mind that carburetor performance can be affected by many other components on the motorcycle. You should consider the exhaust system, intake manifold, intake and exhaust ports, valve size, camshaft lift and duration, combustion chamber design, mufflers, air cleaner, and so on. Alter any of these parts, and activity in the carburetor will probably also change. The carburetor must supply air and fuel to the engine in the correct ratio. This ratio varies depending on engine demand. For example, starting a cold engine requires a rich mixture, but for good fuel economy while cruising, a lean mixture is best. As the piston descends on its downstroke, a low-pressure area is created in the cylinder. When the intake valve opens, air outside the cylinder at higher pressure flows into the cylinder. This, in turn, draws air through the carburetor from the atmosphere. Remember, air under high pressure moves toward air under low pressure if the two areas are connected by an enclosed passage. Now for the fuel. There is a pool of fuel in a float bowl below the carburetor bore. A tube connects this float bowl to the carb bore. You'll also notice that the carburetor bore contains a constriction which is called a Venturi. When air rushes through the constriction, a low-pressure area is created. Remember, air that travels through a constriction increases in speed and decreases in pressure at the point of constriction. Air above the fuel in the float bowl exerts atmospheric pressure. Fuel travels up the tube because of the high force of the atmospheric pressure in the float bowl and the low pressure of the flowing air at the top of the tube in the carb bore. As the fuel meets the air, the fuel is atomized or broken down into fine droplets. That's the basic idea of how a carburetor works. But how do we control the volume of fuel flowing to the combustion chamber? Well, low pressure in the Venturi allows the fuel to move up the tube. So if we can regulate the low pressure, we can help control the amount of fuel to the engine. Remember, we are actually working with a pressure difference between the atmospheric air above the fuel in the float bowl and the air moving through the Venturi. Pressure above the fuel in the float bowl will stay as constant as the outside atmospheric pressure. The carburetor's fuel system works this way. Fuel is gravity-fed from the fuel tank to the float bowl to a predetermined level. Inside the float bowl is a float assembly. The float assembly rises with the fuel until a float valve and seat shut off the fuel flow. The fuel level doesn't fluctuate as in this demonstration, but is actually kept relatively constant. This constant level is necessary when working with the pressure difference between the float bowl and the Venturi. To change the pressure difference, we can vary the size of the Venturi. For example, an extreme constriction would create a much lower pressure area than a slight constriction. In order to gather a large amount of air, the carb bore starts out wide, narrows down into a constriction, and widens out again. The air only has to speed up for a short distance. This cuts down on friction and turbulence caused when trying to move lots of air through a very narrow bore. And that design works out perfectly if we put our fuel tube right where the airspeed is fastest. Right here, at the narrowest part. Again, the law states, air that travels through a constriction increases in speed and decreases in pressure at the point of constriction. So if we choose a particular Venturi size, we can control the airspeed through the carburetor. That means we control the air pressure as well. And since the fuel level is constant in the float bowl, the pressure difference is now completely under our control. Now, we need to control the amount of fuel that is fed to the engine because of the low pressure. This is accomplished with a jet, pressed or threaded into the fuel tube. The jet is exactly the right size to let in the right amount of fuel. There is also an air passage through the carburetor body with an air jet that combines with the fuel in the tube. This adds air to the fuel mixture and promotes atomization. An engine with this carburetor would work, but only at one speed. At this point, we can't give it more air for more power or less air for less power because we've got a Venturi that doesn't change. But if we can vary the airflow through the carburetor, we can change power output in the engine. A throttle plate is the answer. The throttle plate is placed downstream of the fuel tube. Now we can bring in more air or less air to the carburetor. That means we'll send more or less fuel to the engine. Now our engine can operate at different speeds. But to make our carburetor more efficient at all speeds, we need to add more fuel circuits. We said earlier that a lot of testing has gone into carburetor development. Here, engineers establish fuel curves for various carburetors. A fuel curve shows the ratio between air and fuel through an engine's RPM range. Ideally, every carburetor should produce a perfect curve. It would take too much time to explain this concept fully. But basically, people who develop carburetors strive to create one that is completely efficient under all engine operating conditions. One that never allows the engine to run too lean or too rich, and one that meets EPA requirements. From the results of this kind of testing, we've learned that additional features need to be added to our carburetor. For starters, an engine that's idling has different needs than one that's producing power at top speed. How do we design a carb to accommodate all the different engine conditions? Well, a carburetor has several different fuel circuits to cover all bases. These circuits include cold start, idle and low speed, mid-range, and main or high speed. The type of carburetor we've been examining so far in this program is called a fixed jet carburetor. As we explained basic operation, we concentrated on those parts of the carburetor which make up the main or high-speed circuit. That is, the float bowl, main fuel jet, main air jet, Venturi, throttle plate, and internal passages in the carburetor body. This main circuit meets the demands of the engine at higher speeds. It works because when engine RPM is high and the throttle plate is approaching full open, a large volume of air is passing through the Venturi. This means the pressure difference between the float bowl area and the Venturi is great. Plenty of fuel is drawn up the main jet. But what if the engine is idling or operating at low speeds? At lower speeds, with the throttle plate open slightly, only a small amount of air passes through the Venturi. The air is moving slowly, so the pressure difference between the bottom and the top of the main fuel jet is not very significant. The pressure in the Venturi just isn't low enough to prompt fuel to travel up the tube. The solution is to place additional jets and air passages in the carburetor body in an area that will provide a strong pressure difference. As you can see, when the throttle plate is opened slightly, a very small passage is created. The small size of this passage assures that the pressure difference will be strong here, even though it isn't very strong at the main jet. So, additional tubes with jets lead from the float bowl to specific areas in the carb bore near the throttle plate. Some fuel exits on the manifold side of the throttle plate. So even with the throttle open only slightly, engine vacuum will draw some fuel when the engine needs it. At this time, we're going to turn our attention to the constant velocity carburetor. We'll look further into the various fuel circuits a bit later. For comparison, we will refer to the fixed jet carburetor now and then, but in the interest of time, we won't show you every last detail of both carburetors. The main difference between the constant velocity and fixed jet carburetor is a slide mechanism which is able to move up and down into the bore of a CV carb. This slide becomes the Venturi. The slide is designed to adjust the size of the Venturi so that the airspeed stays nearly constant in the Venturi. Here's how it works differently than the fixed jet. In a fixed jet carb, as the throttle plate opens up, more air travels through the Venturi. The air moves faster and pressure drops. That's how we get more fuel into the engine. In a constant velocity carburetor, as the throttle plate opens, the movable slide automatically adjusts the size of the Venturi. So even though more air is passing through, the velocity through the Venturi remains nearly constant. The slide keeps on compensating for changes in the throttle plate position. In the fixed jet carb, the pressure difference changes a lot. The change is what regulates the amount of fuel from the main jet. With the variable Venturi and the CV, the pressure difference is kept almost constant. So, in the variable Venturi, We need a different means to regulate the gas flow from the tube because the pressure difference doesn't change much with engine demand. This is accomplished with a needle and needle jet. The needle attaches to the bottom of the slide. At slow speeds, when the slide is low and the Venturi small, the tapered needle meters the fuel flow by restricting the passageway. But at higher speeds, when the slide is up, the needle is lifted farther out of the tube, allowing maximum fuel to pass. The next question is, what forces actually cause the slide to move up and down? The slide used in Harleys has a rubber seal called a diaphragm, which creates two separate compartments, one above and one below the diaphragm. Within the slide is a return spring. The separation is necessary to make use of the physical laws that move the slide. There's no linkage connecting the slide to an external control cable. Slide movement is based on air movement and pressure difference. If you look at the air cleaner side, you'll find a passage that leads from the outside atmosphere to an area inside the carburetor body underneath the diaphragm. This area maintains atmospheric pressure, and we know that this pressure is higher than Venturi pressure when air is moving through the Venturi. If you look at the underside of the slide mechanism, you'll see a vent hole which leads to the compartment above the diaphragm. So, when the slide is in place, this area maintains the same pressure that's found in the Venturi. In other words, the pressure here above the diaphragm is lower than the atmospheric pressure in this area below the diaphragm. Atmospheric pressure pushes against the underside of the diaphragm at all times. Low Venturi pressure transfers to the area above the diaphragm, and the higher atmospheric pressure is able to move the slide upward. It stops moving the slide upward when the force of the atmospheric pressure is counteracted by the weight of the slide itself and the force of the return spring. We've been talking a lot about atmospheric pressure and pressure differences, and that brings us to high-altitude riding. Because the slide works with pressure differences, high-altitude riding is less of a concern. As you know, a fixed-jet carb set for sea-level riding will run rich at high altitudes. This excessive richness causes poor drivability, low fuel economy, and even spark plug fouling in severe cases. This is normally corrected by changing jets in the fixed-jet carb. But the slide in the CV carb compensates by dropping slightly. This happens because atmospheric pressure is not as great at high altitudes as it is at sea level, so the pressure difference is not as great at high altitudes. The tapered needle drops, reducing the fuel flow. Now let's look at those individual fuel circuits in more detail. These systems are similar on both the fixed jet and CV carb. In the constant velocity carburetor, the idle and slow speed circuit functions when the throttle plate is partially open. The components are the slow fuel jet, slow air jet, the idle mixture screw, and the idle and transfer ports within the carb body. Fuel from the float bowl is drawn up an internal passage and metered by the slow or pilot fuel jet. Air enters the circuit through an internal carb body passage. A non-replaceable fixed air jet meters the air volume. The air and fuel mixture exits into the carb bore on the vacuum or manifold side of the throttle plate. The atomized mixture is regulated by the idle mixture screw. The mixture screw is preset at the factory and should not be altered. However, the throttle stop screw may be adjusted. You'll find instructions in the service manual. As the throttle plate opens further and engine RPM increases, transfer ports are exposed to engine vacuum and help smooth the transition to the mid-range circuit. The mid-range circuit incorporates the slide, the jet needle and needle jet, the main fuel jet, and the main air jet. The fuel from the transfer ports dwindles as the throttle plate opens further because the pressure difference gets weaker. At the same time, the pressure difference becomes stronger in the Venturi over the main jet. As we leave mid-range and enter high speed, the slide rises higher. The needle lifts further out of the needle jet, and more fuel is sent to the engine. At high speeds, the main jet is the dominant supplier of fuel. How do we start a cold engine? The fixed jet carb doesn't have a starting circuit exactly, but employs a choke to make the mixture richer by restricting airflow. The choke system consists of a choke plate, a fast idle cam, and a choke knob, which is operated by the rider. When the knob is all the way out, the choke plate is fully closed. This position is best for cold starts. Basically, the choke plate greatly limits the airflow through the Venturi. When the choke plate is closed, air flows through this small hole in the plate, creating a very rich mixture. Also, as the choke plate closes, the fast idle cam opens the throttle plate, which exposes idle ports and allows air to pass. The rich air and fuel mixture travels to the engine, drawn by low pressure. The system also has warm-up positions and a run position in which the choke plate is fully open. With the plate fully open, the air moves freely past the choke plate and the fast idle cam has no effect on the throttle plate. The CV carb uses a different system called an enricher circuit. The enricher circuit is like a mini carburetor with its own fuel and air passages. Let's identify the enricher circuit components. There's the enricher valve or plunger, the cable assembly, the air passages contained in the carb body, and the fuel jet and fuel passages in the carb body. When the throttle plate is closed, the main jet circuitry is closed off. There's no low pressure affecting the Venturi. So, there is a separate internal passage from the float bowl that leads through the carb body and ends up here on the manifold side of the throttle plate. A non-replaceable fuel jet is pressed into the carb body at the float bowl end of the fuel passage. This jet regulates fuel flow. Now for the air. If you look on the air cleaner side, you'll find a passage that leads from the outside atmosphere to an area inside the carburetor body underneath the diaphragm. This area maintains atmospheric pressure. It's one of the compartments involved in slide movement. On the other side of the slot, you'll see a hole, again below the diaphragm. This hole is a passage through to the carburetor bore that comes out just on the manifold side of the throttle plate. Air under atmospheric pressure travels through this passage when prompted by the low pressure area created by the piston on its downstroke. The air and fuel mix, atomization occurs, and the engine has fuel for starting. No other circuits are effective at this point because the throttle remains closed. The circuit is opened or closed by this cable. The cable attaches to the plunger. When the plunger is all the way in, it closes off both the fuel and air passages of the circuit. When the knob is pulled out by the rider, the plunger opens and exposes the fuel and air passages. One important note: the enricher cable must have the correct tension in order to work properly. You'll find details in the service manual. It is also important that the rider understand how to regulate the enricher. The knob must be returned to the off position when the engine is warmed up and running to avoid a mixture that is too rich. An overly rich mixture could result in fouled plugs and poor fuel economy. There is another system that helps keep the engine response smooth and steady. The Accelerator pump system provides an extra dose of fuel to smooth out engine operation. This system comes into play when the throttle is suddenly opened. It also assists engine operation during warm engine startup. The system consists of the linkage, which controls operation, a diaphragm and diaphragm spring, internal passages, a check valve, and a pump nozzle. The linkage consists of the throttle rod, pump lever, and pump rod. Fuel travels from the float bowl through a small hole, filling a small chamber below the diaphragm. When the rider twists the throttle grip to open the throttle plate, the connecting linkage flexes the diaphragm, emptying the fuel chamber. The fuel is forced through an internal passage which contains a check valve. The check valve prevents fuel from flowing back into the chamber from the nozzle. Fuel flow continues through the pump nozzle and squirts directly into the carb bore. The spring returns the diaphragm to its original position, and the process repeats. Let's review some of the important points we've learned in this program. The carburetor supplies two things to the engine: air and fuel. Engineers study fuel curves to learn how the ideal curve can be maintained. Carburetors must also allow the engine to meet EPA requirements. The carburetor works because of air movement and pressure differences. The throttle plate regulates airflow through the carburetor and makes it possible to run an engine at a variety of speeds. A carburetor contains various fuel circuits that work at different engine speeds. Fuel flow in the various circuits is regulated by the size of the jets in the fuel tubes. The main feature of the CV carb is the slide mechanism, which is activated by air pressure differences. The result is near constant velocity of the airflow through the carburetor, even though air volume increases due to engine demand. A needle and needle jet regulate fuel flow from the main jet in the CV carb. The constant velocity carburetor partially compensates for differences in altitude. As you can see, we've come a long way from the tomato can. We hope you now have a better understanding of this important support system and its contribution to the heart of a Harley.